Okay, today we're going to talk about the history of quantum mechanics and really the development of the material that's in this course. Now, don't be bored by the history. What I'm going to try to do is help you follow mentally through the development from really ancient scientific thought to the current quantum theories. How many people, well, you've seen it, like we talked about last time in the Ant-Man and the Wasp, how mysterious the quantum thinking is. Well, where did it come from? Where did this quantum thinking originate? Because it is a really strange idea if you think about nature only being able to have certain quantized energies. So before we get into the history of it, what do we mean by quantum thinking, or the word quantum? Quantum is just, you could say, a unit of energy. Think of a stairwell. If you're going up a stairwell and you stop, you're on a particular stair. Okay, if you compare that to a ramp would be continuous, and a stairwell would be quantum or quantized. So each stair is a quantized level of energy. And as we've developed quantum mechanics, we see that nature really fits a quantized model of energy. That's controversial if you think about it. Why can't an electron have any energy in an atom? The evidence from the experiment suggests that it can't. So where did this begin? Let's go all the way back. This early 1600s, late 1500s, to René Descartes. And this will be a real quick history. It's expanded a little bit in that paper that I posted on Blackboard, which is chapter 1 for the book that I'm writing. And so I'm giving you guys the chapters that I've developed. Also, I'd like any kind of comments. If you read through that and you say, wow, you lost me at this paragraph, go ahead and let me know, because you guys can serve as reviewers for that book. I'll acknowledge your contribution for proofreading the text when I send it in. But if you see something you say, okay, these words here I'm not getting, or you lost me in this paragraph, I'd love that feedback. Okay. So it goes back, René Descartes talked about the mind, and he was thinking about thinking. That's what philosophers do. And he recognized that the algebra that was developed in really two places in the Middle East, with Al-Khwarizmi and Diophantus, a Greek philosopher, was interesting if you applied it to nature. Now think about that. This is before they thought about applying math to nature. Math was new. That's really strange to think about for us today. Math is in everything. Okay, so he said that the mind has in it some spark of divine thinking, where we have these useful germs of thought, and he thought of mathematics as a useful germ of thought. It's not well developed yet, but there might be something interesting there. And so he started exploring math applied to nature, and he wrote a book on geometry. Guess who read that book and was impressed by it? Isaac Newton. And so he read Descartes' book on geometry, and this is what sparked Newton to apply mathematics to gravity and nature all around him. And so Newtonian physics was born, as well as calculus. And so this calculus, this new way of applying mathematics to nature, carried forward another couple of hundred years. We have Ludwig Boltzmann, and he's looking at entropy. At that point, they had measurements of entropy. They didn't really know what entropy was. And he was applying Newton's calculus to gas molecules and their velocities, talking about equilibrium and entropy. And he used, as a sort of mathematical simplification, the idea that these gas molecules can only have certain velocities. So discrete, if you want to call it quantized velocities. And he said in his paper, this isn't meant to reflect reality, it's just that it makes the math simpler. Okay? And so he kind of quickly said, I'm not saying anything about nature, but I'm just sort of using a mathematical simplification of discrete mathematics. And that's what we're doing in Excel in about 3 weeks, is using discrete mathematics to solve for these wave functions. Well, later on in studying blackbody radiators, Max Planck used Boltzmann's discrete distribution and solved the problem and won a Nobel Prize. Okay? And he's really given the credit for being the father of quantum mechanics, because he used this idea of discrete energy values for the emission of light out of a black body. We'll look in a second what a blackbody radiator is. But he solved that problem. And as like I said, won a Nobel Prize, but also introduced the idea of Planck's constant and what he called the elementary quantum of action. that nature can spit out light or absorb light in these discrete little packets. And if you treat it that way, you match the experiment. And so experiment throughout all of this was guiding our theory. We'd have an experimental piece of evidence that we couldn't explain, and we'd come up with a theory that would match it. And that's what led to this quantum idea. Of course, Werner Heisenberg came onto the scene, and he solved a lot of these problems using matrix mechanics or linear algebra. Now, if you've taken linear algebra, or if you ever do take linear algebra, you'll notice that matrices have some interesting properties. That if you take a matrix A and multiply it by B, you get a different result, but perhaps if you take matrix B and multiply it by A. So you can't flop A and B like you can in normal algebra. Like x times y is the same as y times x, but not if x and y are matrices, not always. And that's called commutation. It's the rule of commutation. And so because position and momentum didn't commute, their matrices gave different answers depending on the order in which they were multiplied. This led to Heisenberg's uncertainty principle. So you've heard of Heisenberg's uncertainty principle, perhaps? It was that difference between A times B versus B times A, and it came right out of Heisenberg's mathematics. And so this was really controversial because it put a limit on what we could know about nature. If we specified the momentum of a particle, we really didn't know anything about its position, and vice versa. This was also translated over into energy and time. If I want to know the energy exactly of a particular system, I would have to look at it for a near infinite amount of time. But if I look at it instantaneously, I really don't know much about its energy. This wave nature of light versus particle nature of light started to become controversial. We'll learn about the Bohr atom. So Niels Bohr, in looking at the hydrogen atom emission, said, well, what if this is like a planetary model? And he created a sort of a solar system model of the atom, where you have a proton in the middle and you had electrons around it. And yet that still didn't explain how the electron stayed out of the nucleus. Because if an atom was like a tetherball, and if a charge like an electron is oscillating around a circle, that oscillating charge would emit light, electromagnetic radiation. And it can't, you don't get, light's not free. If it's emitting light, it's dropping in energy. And so it would spiral down into the nucleus. What kept it out of the nucleus? So I used to call him de Broglie, but I read it in his book. It's de Broglie. So de Broglie came along, and he was a lover of classical music. And he thought, what if the electron in orbiting the nucleus is a standing wave? And so he introduced this concept of waves, in that the electron had a certain number of waves that in its orbit, and that it couldn't shrink because then those waves wouldn't line up. And so this standing wave model was introduced by de Broglie, and he came up with the Broglie wavelength. So this is another germ of useful mode of thinking. He introduced that maybe some of these electron orbits can be described using waves, standing waves. And so this was complemented, because it matched the data, by Einstein in a paper. And then Schrodinger read Einstein's paper and pulled de Broglie's idea forward. And so Erwin Schrodinger took this wave idea and solved the problem for the hydrogen atom. And then Dirac took Schrodinger's idea and added in time dependence and made it compatible with Einstein's theory of relativity. So that's where we are today. You're going to hear the name Dirac through the whole course, because we're going to use his notation for doing integrals. And so let me just show you that very quickly. Let me flip to a different scene here. I think it's scene 5. Just make sure. Okay, yes. We can see that fine. So when I talk about Dirac notation, if we have the integral of a wave function, and we'll define what these are later. So these wave functions are a function of x. And so we're integrating over all space with respect to x. And to simplify this notation, Dirac just used these brackets. this. And so these two things are the same. So this is Dirac notation, and we're going to use it throughout the course. Can you see that over on the right? Is that good for you? Okay.
So the bottom one is Dirac's notation?
Yeah, this is Dirac's notation. So these angle brackets, this line in the middle means that the wave function is multiplied by each other. Okay, so the wave function on the left is multiplied by the wave function on the right. Another thing, too, we'll unpack later is this little star here. Looks like an X. It should be a star. There's a little section in the notes on Blackboard that talks about imaginary numbers. These wave functions that we're going to deal with, and then we're going to explain to you in the future, can be imaginary. They can have imaginary numbers in it. And so this star is what's called the complex conjugate. So it's the wave function, and it's multiplied by its complex conjugate, and then integrated over all space. And so this would be Dirac's notation for that. We will definitely cover this more. I'm just sort of introducing Dirac's notation, and there's Dirac in the previous slide. So let's go back through and look at some of these experiments, like the Blackbody radiation experiment. And so this is the example of the Blackbody emission. So what we have on here are these different curves, and this is wavelength. So out at long wavelength, we have a little bit of light. Shorter wavelength, we get more light being emitted. And then as we get to very short wavelengths, the light that is emitted drops back off to zero. Ready? Can everybody see that? And what we see, this black line here, it says increasing temperature. And so we notice that as you heat an object up, what happens? So you go to your electric stove, you turn it on high, what happens? It starts to glow orange, okay? It starts out, if you pay attention, the next time you cook something on the stove, go ahead and pay attention. It starts out more red, and then it gets closer to the yellow. So it gets red, dimly red, and it gets orange. You can get it to yellow. But you probably have about a 1,000 or 1,500 watt heating element. If you could put more watts through that, you might even get it on up into white hot, where it's emitting all of the wavelengths of light in the visible region, and it looks white hot. So that's what's going on with a blackbody irradiator. Now, does it matter what that heating element's made of in terms of the spectrum? And the answer is no. It's just a function of temperature. So this was a mystery to Planck and all the scientists of the day. Why does hot iron give off the same wavelengths of light as hot tungsten or hot steel or hot zinc or hot ceramic? They all give off the same spectrum. And it's just a function of temperature. If I increase the temperature, I get the same spectrum. It just shifts over to shorter wavelengths of light. Well, this was attacked by several scientists. Wein's displacement law tracked this black curve here, the temperature maximum. And so essentially it acknowledged that it went off to zero on the short wavelength side, and Wein's displacement law would give you this maximum here. So the wavelength, the maximum wavelength of emission times the temperature was these fundamental constants: Planck's constant, the speed of light, and Boltzmann's constant. Sir Rayleigh and Jeans came along, and they fit the long wavelength side using a classical model, what they call equipartition, which we'll get into in the spring. An equipartition model fitting these the elements in these blackbody irradiators would match the long wavelength side, but it went to infinity as the wavelength went to short wavelengths. If you'll notice here, this is the Rayleigh-Jeans law. Notice how it goes to infinity as the wavelength goes to UV light. That's a problem. In fact, it's such a problem that when the experimental data goes to zero and your model goes to infinity, that's a catastrophe. And so they call this the UV catastrophe. That's sort of the pejorative term that they use to describe the Rayleigh-Jeans law. So when you hear UV catastrophe, that's the Rayleigh-Jeans law. It goes to infinity in the UV region where the experiment goes down to 0. And so then Max Planck applied Boltzmann's quantized energies to the Blackbody problem and solved it. And so here's here's Planck's equation, and it matches the experimental data. And down here in the bottom, you see this hc over lambda kT. So kT is Boltzmann's constant times the temperature. And this right here is the quantized piece. Okay. And so by using this concept of quantized energies, he was able to solve the Blackbody problem. And like I said, that led to a Nobel Prize shortly thereafter. This was early, this was 1900. So let's look at this idea of blackbody radiation. This tells us that even at low temperatures, objects are emitting light. And that's the whole point of our night vision goggles, right? Is every object, as the atmosphere cools, everything else looks hot compared to the atmosphere. And you can put on these goggles that are sensitive in the infrared, and you can see the light emitted by trees, and you can see a lot more light coming from warm-blooded animals. If you're hunting hogs, or if you're in the police looking for a runaway that's hiding in the woods, you can use the FLIR system, the infrared camera, and you can see this hot object in the woods at night, because everything that's above absolute 0 is emitting light. It's trying to come to equilibrium with its surroundings. And so that's what, and also certain materials may be opaque to visible light, but transparent to infrared. So here's a person with his hand in a black plastic sack. You can't see through it, but you look in the infrared, you can see the arm and the hand. And so that's the infrared light coming off of this person's hand, going through the plastic bag. So there's a lot of fun things you can do with cameras that are sensitive in different areas of the spectrum. This is really good for forensic analysis. Changing the wavelength at which you're detecting is very good at enhancing contrast. Over here we have no contrast related to his arm, but over here we have excellent contrast. You can even see that he has all 5 of his fingers. So this blackbody radiation is really very useful, and also is the experiment that really led to quantum thinking. It was not even well received by the person who used it. So Max Planck said this was an act of desperation. He struggled with this problem for 6 years. So you think you have mathematical troubles? How many people studied a mathematical problem for 6 years? Okay. And so he knew that the problem was fundamental, and he had to find a theoretical explanation. So his explanation was that energy is quantized. At least it's emitted and absorbed in quantized packets. Some of these discussions, this early science, was done at the Solvay conferences. And so here's Ernest Solvay. He was a rich industrialist, and he was interested in physics. He thought physics, because he was an industrialist, held the key to future advancements, and so he wanted to fund physics. And one of the things that he would like to do is have people at his enormous estate, and he would invite the most famous physicists of the day, get them all in the same room so that they could share ideas. So this is which one is this? The first Solvay conference in 1911. And so you recognize some of these names probably. Here's Max Planck. Here's de Broglie. Okay. And number 3 is Jeans from the Rayleigh-Jeans law. Here's Ernest Rutherford, the discoverer of the nucleus. Here's Albert Einstein. And then seated over here in 6 is Ernest. Let's see, 6. Nernst, from Nernst's law, from Gen Chem, when you were talking about electrochemistry. Here's Solvay. Number 8 is Wilhelm Wein. Here's Marie Curie. That's fantastic. So, and also all of the ones that I haven't kind of pointed out. You've got Lorentz, Brion, just a lot of well-known names. Sommerfeld was a mathematician that pretty much taught everybody else math. So, talk about an unsung hero. He's the one that really advanced the science. So Max Planck talked about this elementary quantum of action, this H, this Planck's constant. And so this is Planck's equation here, that this change in energy, this photon that's coming out, although we really didn't have the term photon at the time, this light that's coming out is in discrete packets, and it's related to the frequency. And so if you take that frequency and multiply by Planck's constant, you get the energy difference. So when I'll talk about the Planck equation, this is the Planck equation. Well, you could shine light on a metal surface, and electrons would come streaming off, and you could detect those electrons, detect their charge. And if you change the frequency of light, you got more or less electrons. And so this essentially confirmed Planck's law. What do you think the slope of this line is? Here's frequency of incident radiation, and here's the kinetic energy of the electrons that are spit out. The slope, if energy is equal to some linear relationship related to frequency, that slope of that line is Planck's constant. So immediately we were able to measure Planck's constant using the photoelectron experiment. Okay. Now how does this relate to wavelength? Well, this is one of my catchphrases. When I see you on the sidewalk, walking around on campus, and I ask you what's new, what do you tell me? C over lambda. Right? Okay, and I definitely test you on that. In rare times, and we just, unexpected times, we're walking across campus, hey, what's new? C over lambda, okay? And if somebody else asks you what's new, you can say C over lambda, and they'll look at you. They're like, you had Williams, right? Definitely. So this photoelectric effect, when you hear about photoelectric effect, just break the word into its parts. Photo, light, electric. So light hits an object, electrons come off. Okay. This also lent credence to Newton's idea that light was a particle. Because they really didn't know what light was. Newton said it was a particle. Huygens, a famous scientist of the day, said it was a wave. And everybody made fun of Huygens. They're like, that's ridiculous. In fact, Thomas Young, the diffraction experiments, he gave lectures in 1801 to 1803 on the wave nature of light with diffraction, and the Royal Society pretty much laughed him out of the room. They said his paper was destitute of all merit for suggesting that light was a wave. So everybody thought that light was a particle. And this pretty much confirmed it, because if light's a wave, how does that whole wavefront get absorbed by one electron and leave? Have you ever been body surfing? Wouldn't that be weird? You get a good wave, you catch the wave, and the whole energy of that wave collapses, and you come flying off the beach over the seawall, And so that really didn't make conceptual sense that light could be a wave. How could all of that energy of that wave, which typically the energy of a wave is dispersed over the wave, and be collapsed into a single particle? So this really lent credence to the particulate nature of light. This is the source, this photoelectric effect, the mechanism for all of our photomultiplier tubes. So in your visible experiments, and even some detectors are based upon this, and in the infrared, if you cool things down, light comes in, and you have a voltage here, and electrons come off, and you detect those electrons. And so photomultiplier tubes in our visible spectrometers, they're using the photoelectric effect. The photoelectric effect is very useful for determining bonding characteristics. So if you hit a substance with light and detect electrons coming out, they don't always come out with the energy of the light that you put in. They come out with a smaller energy. Where'd the difference in energy go? Well, it's telling you how deep in the electron cloud that electron was. So if this is the depth of that electron, let's say an orbital or whatever, and you hit it with light, if this is the depth that electron is in, and you hit it with light that's below that threshold, you won't get any photoelectrons out. But if you hit it with more light than you need, so this is the depth of the electron in the electron cloud, and you hit it with light that's much more powerful, then the electron comes out with kinetic energy that tells you how deep it was. So this is the foundation of what we call photoelectron spectroscopy. If you want to get down to the core electrons, like the 1s electrons, it's X-ray. So X-ray photoelectron spectroscopy is incredibly useful for determining what types of elements you have in a substance. Because if you look at the periodic table, notice the blue numbers here are the number of protons. And so every element has a different number of protons. That's what defines an element. Where's the 1s orbital? Very close to the nucleus. And so the 1s orbital knows the most about the nucleus. And so if I use X-rays and I yank electrons out of the 1s orbital, I get a different energy, a different kinetic energy for every element on the periodic table. And so this was Moseley's law. Moseley came up with this relationship between X-rays and 1s electrons. They didn't really have the terminology for 1s, okay? But these electrons that come out of different elements, and that's how we filled in the rest of the periodic table, using Moseley's law. Because we would see the elements that we had, it was this linear relationship. We hit it with X-rays, and we get all of these energies, and then there'll be a gap, and then we have another element up here. Well, you've got a gap that has about 3 elements of space in it. We know there's 3 elements there that we haven't discovered yet. Okay, this is awesome too, because I don't need to get a weighable mass of that element to discover it. It could be part of a mineral, and I could hit that mineral with X-rays, and I could get all the elements that I know, and I find one that's in a gap. Hey, I've discovered a new element. It's in this mineral. And then I could get more of that mineral and then start to isolate it and try to discover what its other properties are. So this X-ray experiment was really key in filling out the periodic table. Now that 1s electron tells you just about the nucleus, essentially. I could use UV light and get the bonding information. So throughout this whole course, when we talk about bonding, one of our best probes is photoelectron spectroscopy. UV photoelectron spectroscopy, or UPS or UVPS, would be good for bonding. X-ray photoelectron spectroscopy would be good about elemental identities. So then they kept having Solvay conferences. This one is the one in 1927, and this is when quantum mechanics was really being developed, and so we have a different set of players. Now we see folks like Schrodinger. Okay, so he's here. Here's Schrodinger, number 1. De Broglie still here. This is Heisenberg. Over here we have Debye, who the dipole moment unit is named after Debye. Let's see, number 6 is Bragg diffraction. If you're taking instrumental analysis, you'll talk about Bragg diffraction. Let's see, 7, here's Dirac, so he's shown up on the scene. Here's De Broglie, here's Max Born, and here's Niels Bohr. Here's Planck, he's still around, Madame Curie, and Einstein. You start to see some of his age now. Okay, this is 1927. So the hydrogen atom still was a difficult thing. We had the photoelectric effect, we had blackbody radiation, but hydrogen is the simplest atom on the periodic table. 1 proton, 1 electron. They still do not understand its emission spectrum. How do you get the emission spectrum of a gas? You run electricity through it, just like our mercury tube lights. And what's interesting is this high voltage discharge tube, you could just use a flame, and you could put elements that are dissolved in water into a flame and see their emission spectrum. And then you run that emission, you narrow it down with a slit, you put it through a prism, and disperse it on a photographic plate. And what's amazing is this is pretty complex. This is a spectrometer. It's a slit, a dispersing element like a prism or a grating, and then some sort of detector. And photographic film is as good as anything else. It's what they had in the day. And Bunsen invented this. He invented the spectrometer. But he's credited with inventing the little flame device that he put the elements in. So the Bunsen burner was this piece right here. Now we have it all in a quartz tube, and we run voltage through there, so we don't have to constantly get our gases or our elements. But, you know, we kind of missed the boat. I think Bunsen should be upset about that. He invented something way more interesting than a burner. Okay, but that's what he's tasked as inventing. So notice that this spectrum of hydrogen is not a continuous rainbow. It's discrete lines. And why are they called lines? Well, the slit here created a vertical beam of light, and that beam of light exposed the film, and so it's really the image of the slit on that film that gave us this line idea. And so when we talk about spectral lines, that's one of the #1 vocabulary terms in this course. We're talking about the lines in a spectrum, a particular transition. Okay. A transition. What does the transition mean? Transition between quantized energy states. So in order to try to explain this, they had to come up with a model for the atom. And so we had this crazy idea that these electrons are orbiting the nucleus. But if you've ever played tetherball, anybody ever played tetherball? Okay, it's this right here. It's a pole with a string and a ball on it. And you hit that ball, and it doesn't stay in a quantized orbit. It slowly drifts down. That angle moves slowly. It'd be great to have quantum tetherball. Okay, you hit it and it spins like that, and then at some unknown time, it's going to transition to boom. Okay, okay, but it's discrete. So you hit it again and it pops up. Okay, and it drops down. Okay, and so this is quantum tetherball. You know, it's spinning like this, and then it drops down instantaneously. So you're ready to hit it again, and it drops down, and you miss. So that would be really an exciting game of tetherball. But the atom is not like classical tetherball. These electrons orbit at a certain distance from the nucleus if they're excited and are electric discharge, and then boom, they jump down and emit a photon of light. And that photon of light always has the same frequency, and it exposes that film at a particular line. And Rydberg and Balmer looked at these lines and they said, you know, we could fit this to an integer series, but we don't know what those integers are. So they actually discovered quantum numbers. But they didn't know the idea of quantum. They didn't know why it would be an integer series. But de Broglie said, okay, this Bohr atom where you have these orbits, what if those are standing waves? And you can bump an electron from 1s, give it a few more nodes, and now it can be out in a 2s orbital. And we came up with these terms later, s and d and p and so on. And so this idea came from de Broglie, was picked up by Schrodinger, and turned into the Schrodinger equation. So this is Schrodinger's paper. It was one a little bit earlier than this, but this one is fully developed. The undulatory, which is the wave theory of the mechanics of atoms and molecules, and he solved the hydrogen spectrum. So he took the wave idea from de Broglie, he took Rydberg's constant and the integer series of all of those jumps in the hydrogen atom, and he wrapped it all up and came up with quantum mechanics. Then Dirac came along and expanded it a little bit, and here's a picture of Dirac's paper. Okay, and I have these. You can have copies of these if you want. It's kind of neat just to read the original papers that discovered quantum mechanics. And so this has a really nice quote in the abstract. You know, now that we'd solved the hydrogen atom, and we had photoelectric effect and blackbody radiation, all of these really difficult experiments had now been solved in about 30 years, from the 1900s to 1930. He says the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry is thus completely known. Okay. The difficulty is the exact application of these laws leads to equations much too complicated to be soluble. Yeah, I hear you. Okay, these equations are a mess. In fact, it took Schrodinger about 3 weeks to solve the hydrogen problem, and he had to actually get help from Hermann Weyl on the differential equations. And so what does Dirac call out for us to do? He says, well, it therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed. So practical methods that are approximate, which can lead to explanations of the main features of the complex atomic systems without too much computation. Right? Yay, I like that idea as well. And so that's where my book comes in. Okay. So I'm trying to write this out. So what you have on Blackboard is the introduction of this book. Chapter 2 is written as well, called Managing the Messy Mathematics. And that's what we're going to do next week. We're going to manage the messy mathematics. We're going to do it in one dimension. And so by analogy, from one dimension onto 3 dimensions, we'll use symmetry. And that will allow us to take our thinking about what happens with a guitar string, a one-dimensional wave, and we can rotate that around in 3-dimensional space, and we can get an atom. We can bring atoms together, and we can see how these waves would interact with symmetry, and we could get molecules. Okay, so we'll do the heavy lifting mathematically with one dimension, and then by analogy we'll expand it to 3 dimensions. So look forward to next week.